Tom Fitzpatrick from Mentor, a Siemens business, is strategic verification architect at Mentor, where he works on developing advanced verification methodologies and educating users on their adoption. He is currently responsible for Mentor's safety-critical verification strategies and has been a significant contributor to several industry standards. He holds a master's and bachelor degree from MIT and currently serves as the vice chair of the Portable Stimulus Working Group and has published multiple articles and technical papers. Thank you, Tom. Over to you.
Great, thanks, Sarah. All right, hi, everybody. I sure hope everybody that's outside of Massachusetts is having better weather than we are. So let's go ahead and get started. So we're going to talk about portable stimulus, moving from IP to SoC with inFact. So even though I am the vice chair of the Portable Stimulus Working Group in Accelera, I am speaking on behalf of Mentor today. I might let a little bit of inside information slip from the committee, but not much, so bear with me. All right, so the test challenges that people have in going from block to SoC are really to be able to productively create high quality tests, right? We want to be able to find bugs early. We want to maximize the coverage of our stimulus space. We want to generate the required stimulus with the minimum amount of user guidance. And really we do a survey every couple of years here at Mentor to find out the state of things in the industry. And the biggest verification challenge that is continually reported is the ability to create sufficient tests to achieve coverage closure. So we're going to talk about that a lot today. The other thing that I'm sure you've all seen is that we need support across many different test environments. So we need to support C++ for high-level synthesis, UVM for block level up to subsystem, and then when you get up to the SoC area, you're really talking about running embedded software. So that same survey showed that 72% of ASIC designs today contain embedded processors, and 59% of FPGA designs also contain embedded processors. So if you're not there yet, you will be, and you need to be able to have embedded software to drive your verification as well. So a lot of that typically is directed tests, which are kind of focused, but they're pretty low productivity. And we want to be able to take advantage of constrained random tests, which typically require a fair amount of user guidance, particularly when you start trying to put things together. And that's really why constrained random tests don't easily scale when you get up to the system or to the scenario level. So we want to be able to address all of those things. The vision of portable stimulus is that we have this single specification of our test intent. So we want to be able to use tools and automation to support that test intent going all the way from the block up to the SoC level. So whether you're on simulation, emulation, FPGA prototyping, virtual prototyping, whatever, we want to be able to support that test intent on those multiple engines. So the idea is that we capture a scenario space, which is sort of the operational sequences, all the resource dependencies, and the data constraints for your scenarios, and rely on automated test generation to be able to create those scenarios for your given environment that will hopefully get you to your verification goals more quickly. And that's really the intent behind inFact, right? So we've talked a lot over the last couple of years when we've been presenting portable stimulus about the fact that it's a declarative specification. So kind of what do we mean by that? So as I said, most SoC tests are directed. It's kind of like taking a paper map, if you remember what those are, and manually determining your turn-by-turn direction. So you're going to start in Providence, go down to Baltimore. Apologies to those of you not in the US. It's just kind of a long drive, and there's lots of ways you can go. So you kind of say, okay, I'm going to start here. I'll go to the first big intersection, figure out where I'm going to go from there, and then go to the next one and kind of figure that out. It's kind of hard to account for new variations, so if you've plotted a whole path and then, your buddy says, hey, can you give me a ride and drop me in Hartford or wherever, you have to kind of redo a lot of that. So the other thing is that the route is limited by the driver's biases. So if you're going in a particular direction, you might have been there before, you tend to take the same kinds of roads. So you're sort of less likely to kind of explore other possibilities because you might be afraid that you're going to get into some bad neighborhood or whatever. So you tend to stick with what you know. With a declarative test, on the other hand, you're kind of letting the tool do the work. So it's sort of like going to Google Maps and saying, I want to start in Providence, end in Baltimore, figure out how to get there. So it'll explore all possible options. It's easy to optimize if you throw in another another stop along the way. It can figure out the best way to get there. And it's kind of guided by preferences. So it always asks, do you want to avoid toll roads or not, that kind of thing. So there's a lot of ways of exploring all of the different possibilities, and you can use preferences to kind of keep you out of the bad neighborhoods and that sort of thing. So with portable stimulus, this declarative description enables automation and enables us to analyze what it is we want to do before we go and do it. So it's the automation that really makes the test intent portable, because we're going to use automation to generate the implementations of those test intents on our different platforms. So it enables retargeting to different environments, whether you're talking UVM or a C-based environment, and it makes the same test techniques portable as well. So if you're talking about functional coverage or those kinds of things, that becomes portable. And again, what we're really sort of doing is using this automation to bring the idea of constraint-driven tests up to the SoC level. Right? And this is something that's going to be extraordinarily valuable, and I'm sure you're going to see a lot of that kind of talk today. So just to kind of set the context for where we're at, portable stimulus actually started way back in 2003. The first commercially available tool was inFact Intelligent Test Bench by a company called Lighthouse Design Automation. Mentor Graphics liked that company so much we bought them in 2006, and our first Quest to inFact release was in 2008. Since then, there have been other tools that have come out, and in 2014, Accelera formed a portable stimulus proposed working group, which essentially did a feasibility study to see if there was enough technology out there to make it worth standardizing on the idea of portable stimulus. And with contributions from a few other companies, as well as inFact and a lot of user input as well, we determined that it was in fact feasible, and in 2015 we formed the portable stimulus working group. So we actually took pieces from each of these, the existing technologies, as well as some feedback from users, et cetera, and started working on a standard. So we developed the early adopter standard last June in 2017. We did an EA2 back in DVCon US in February, and we did 1.0 this past June. So we are continuing to work in the committee. We did kind of slow down a little bit over the summer. I hope you can forgive us for that. And we're currently working on an errata release just to clean up some things in the 1.0 version. So that's sort of where we're at with portable stimulus. With inFact portable stimulus, what we're really focusing on, again, is this idea of efficient as well as portable stimulus moving from the IP to the SoC level. So if you're using system Verilog stimulus today, we want to get you better transaction level stimulus. So we'll reuse your existing class and constraint descriptions. We'll talk a little bit more about that. We can automatically generate system Verilog cover groups for you, and we will integrate into your transaction level system Verilog environment, whether it's UVM or otherwise. So as we'll talk a lot about, we're really kind of generating stimulus that is going to efficiently target your coverage goals. So if you're using simulation, we will generate that. So we will use this idea of the kind of the rules that are defined as part of your portable stimulus definition to efficiently capture these high-level scenarios, and we can integrate it into UVM as a virtual sequence. We can also integrate it into your existing C and C++ environments. So again, we're going to target your stimulus goals as we generate the tests. And when we get up to SoC verification and validation, we're going to reuse that same rule-based scenario from the subsystem level, generate the embedded C tests, and we're going to call your existing test APIs. So right, you can use your existing driver code or whatever and call it in interesting ways. Or if you want to get down to the low level, you can actually create some of that stuff with portable stimulus as well. So in a constrained random environment, which we've been focused on for the last decade or so, probably more, the idea of functional coverage is you identify the critical states that you want to have happen, and then you randomly go and run through your state space and keep your fingers crossed that you hit one of those coverage points eventually. You're never really going to know exactly how you do it because of the randomness of the scenario, but if you run enough tests, you will eventually hit your coverage goals. You're probably going to repeat a lot of stuff as you go. That's just sort of the nature of randomization. But you will eventually get to the point where you've hit your coverage points, and you can use a tool like Quest Verification Management to identify which tests actually hit those coverage points. So for a given scenario run in your simulation with a given seed, we can recreate that exact same test that same path through your state space, if you will, to hit those coverage points. So you'll eventually get there. So after you've run all of your stuff, I hit your coverage points, you can identify those tests and rerun those, make that your regression or whatever. But when you do that, there are a number of states that you may have missed as you've gone through that. And it may be that a given state that you didn't hit is hiding a bug. So it's important that we be able to identify those kinds of things. So with inFact and portable stimulus with functional coverage, we're still using functional coverage to define those critical states, but we're using that as part of our analysis. Because of the static declarative nature of the description, we can look at the graph, identify how to target your functional coverage first, generate those tests first and run them, so we get the maximum coverage in the fewest number of tests. So you'll notice before we had 3 tests that managed to hit our functional coverage points. Here we've got 4 tests that hit all 4 coverage points in different orders. So that's sort of maximizing our coverage in 4 tests. We can run those, and then inFact allows you to sort of say, okay, now that I've hit my coverage, let's go explore and see what else is going to happen. And we'll actually hit all of the possible states that are going to happen. So when you look at all of these different ways of running through your state space, each traversal is effectively a directed test, but when you put them together, because you've hit every possibility, you've effectively randomized everything. So even though you can analyze the graph, figure out what you need to do first to meet your goals, do that more quickly, and then go off and find other things that you hadn't thought about. And that's really where the value comes in something like this, is because you're guaranteed to hit all those other states, including the ones that might have the bug that you'll still find, even if it's beyond the scope of your functional coverage initially. So inFact does this all the time. It's been doing it for years. And it all comes from the ability of having this declarative specification to be able to do the analysis up front, right? So the state space that you're going to wind up with is typically huge, right? Billions and in some cases trillions of possibilities. So we want to be able to focus things and maybe target hundreds or thousands of possibilities. So that's what coverage strategies are all about. So by specifying your coverage up front, for this regression, for these set of tests today, I want to identify the key stimulus values and ranges, the key stimulus combinations and sequences that I have. So then inFact will generate those specific tests for you to limit what you need to do to hit the things that you really care about. And then later, if you have time, you can go beyond that and see what else is going on. So we call this goal-driven systematic generation. So we're going to automatically suppress redundant stimulus. Therefore, we can target your key cases and achieve your goals 10 to 100x faster than random. And also, you will explicitly verify more cases because you have that capability. So the other thing we need to do is to kind of get you started and sort of reduce the time to develop stimulus in the first place. So we have an integrated development environment that lets you figure out where you are. It's all content assisted. So as you're typing, it'll figure out where you are, and then you can actually go and look at the graph that you've created, see if it makes sense. We can leverage your existing system Verilog investment. We'll talk a little bit more about this in a minute, but basically convert all the stuff in your system Verilog UVM environment into portable stimulus. So really kind of get you jump started in portable stimulus. As I said, we statically analyze the scenarios so we can look at your coverage and your constraints. We can make sure that you can actually reach all of those key cases and do some what-if analysis. And we recently added a constraint explorer. So we're going to short circuit the debug loop. So we'll actually look at all of your constraints and tell you before you go and start your simulation in a few seconds whether or not you have any constraint problems. So you go into your simulation knowing that your constraints and your coverage goals are good before you go off and start simulating and figure out that you had a problem. So the stimulus generation really is flexible as well. So we have two, I kind of want to say scenarios, but two use models, if you will, right? So in your existing regression run, we're going to generate all of these different tests, and each test is going to be allocated to a different simulation in your regression farm. So by having this set of tests, your new stimulus is going to be achieved by running with different seeds, so you maximize your verification value. So you basically have one test, one piece of code, which is sort of what we've been talking about for years with a constrained random. Now we're up at the scenario level. You have your test, and each unique generation of that test is run on a different simulation. So you have essentially a centralized engine in inFact, and each simulation will go back to that central engine and say, what's the next value that I should generate? And inFact will keep track of what each of these simulations is doing and reply to each one with a unique scenario as it goes through. So each individual simulation is going to be still a different traversal through your state space, all managed through the centralized inFact engine. And we can do that when you're running simulation because you have the ability to interact with things. When you get up to SoC, where you're actually going to be running C code at this point, then we have to pre-generate the test. So the length of the test is determined at generation time. You do have individual tests, so you have more source to manage. And each test every time you run is going to do the same thing. As I said, each individual traversal is its own directed test. Effectively, when you combine them, you get the randomization. So, so this can become your golden test suite. So effectively, each simulation now is still going to run its own scenario from the centralized engine that generated the tests a priori. Right? So in either case, each individual resource in your simulation or regression farm, prototype farm, whatever, is going to run its own scenario. It's just that we get there different ways. As far as the user is concerned, it's still the one scenario or set of scenarios that were created, and the test automates the generation from there. So when we go from IP level, we're at the block level, we're looking at functional coverage. We want to be able to reach coverage closure efficiently and really start thinking at the block level about these scenarios and start to create scenario level tests. When we get to the subsystem level, it's all about integration. We want to be able to create things like cache-aware traffic and then take some of the IP level scenario tests and bring those in. So in this kind of an environment, most of the stuff is going to be generated from VIP. We can coordinate the traffic between those VIPs. And we have a new tool that does system level performance analysis, so we'll be able to see what's going on. We'll talk about that a little bit more in a minute. And then at the SoC level, you again want to be able to reuse those integration tests, but we want to use them as embedded software because we have our processors that are that we're running on. So we can expand these scenarios to fast execution platforms, whether it's emulation or FPGA prototypes, and take advantage of the infrastructure that we've built up along the way and reuse that and do hardware software debug as well as doing all the other analysis that we can do. All right, so the intent of what you're doing gets reused all the way from the block level up to the system level. So you're taking advantage of the stuff that you put together earlier on as you move up to the SoC level. Even though the generation is now targeted at a different platform, you're reusing a lot of the infrastructure that you created at the abstract scenario level. So at the IP level, again, you're talking about comprehensively exercising your verification IP. We can import all of your system Verilog, your sequence items, cover groups, et cetera, to create that portable stimulus model for you. So we will target those constraints and those coverage goals, and it preserves your consistency with your existing system Verilog, right? So if you want to continue using that as the basis for your portable stimulus model, you can do that. So you only have one set of, golden files, if you will. You can do it that way if you want. And we integrate into a UVM sequence. In simulation, we replace the call to randomize in between start item and finish item with a call into the inFact engine. And then this just runs as another sequence in your UVM environment. So we automatically generate all the sequence and wrapper infrastructure to do this. And as far as you're concerned, it's just another UVM sequence that you're going to run. So we're raising the abstraction level in UVM to compose these higher level scenarios. It's a lot easier to create a virtual sequence in UVM using portable stimulus and inFact to get that scenario level randomization rather than trying to do it the old-fashioned way, if you will, with UVM. The results that we get, and this has been documented many times with our customers, is that we achieve our coverage much more quickly. So using random stimulus and functional coverage, you might hit 100% on some things, but not a lot. With inFact, you generate 100% coverage immediately. It's essentially a linear progression. So you get to your coverage, and then once you've hit your coverage, as I said before, you can relax things and go off and look at and see what else is available. Okay, so we expand the scope of our functional coverage. We also can look at your model and determine where useful coverage bins might be. So, dividing your address space into bins, identifying where your page boundaries are, or FIFO overflows or things like that. So we can actually create additional coverage bins that we know are going to be helpful to you, and we'll generate tests to target those as well. So you get more comprehensive verification as well. And then, as I said, doing that, you can go look, after you do that, you can go look for unexplored corner cases as well. At the subsystem level, we're going to generate interconnect performance traffic. So again, everything is driven from VIP. So we can look at arbitration priorities, cache sizes, and we use the scenario level portable stimulus and inFact to stress those interconnects in realistic ways. So if you want to run these in a UVM environment at your subsystem or at the SoC level as C tests, you can do that. So we can look at all the different traffic between all of the masters in the system. It becomes far more comprehensive than directed tests because it's those interactions that are hard to predict that are where the problems are, and we'll do that for you automatically. So we take your graph, create from there individual sequences that will run on each of the different VIPs to go and generate all those scenarios. And then we can look at the interconnect performance. So this is a screenshot from our system level analysis tool. You can look at all of the transactions that occurred, follow the data flowing through your system, and identify things like average latency and all that stuff. So you can look and find out that, through all of the scenarios that you ran, there was one transaction that took a long time. So we can actually identify where that is, what test it came from, and then go and blow that out and see what else is going on in the system and figure out what happened and why it took that long. And maybe you were just about to clear the cache or something before something else came in or whatever. So we can actually take you down into the details and go from here down into the waveforms and actually see what's going on in your system. So at the SoC level, again, we're going to now pre-generate all of these tests that we have. We can partition them in inFact to either generate more short tests or fewer longer tests. And again, we're going to ensure your full test coverage, even though you're now running C code at the SoC level. So we're going to take your portable stimulus description and inFact, generate a suite of tests for you, and run each of those on the embedded processors in your final system, whether it's an FPGA prototype, emulation, whatever. Right, so Mentor really is all about portable stimulus here, right? So all of the different platforms, all of the different layers throughout your verification. You can verify more with the same resources. So we're going to boost your productivity in creating stimulus in the first place. We can target the stimulus that you care about. We'll actually, we can create some of those scenarios for you. We'll automatically generate stimulus across the environments. And again, we're going to automatically generate interesting coverage points for you that will even take you further than what you might have originally specified. So it's easy to get started. You can reuse your existing system Verilog. You can reuse your existing infrastructure. And we have a number of resources available already for you. There's a portable stimulus video course on Verification Academy. There's a number of Verification Horizons articles. We have the Verification Horizons blog. And there's also a forum on Verification Academy where you can ask questions and get answers. So, so speaking of questions and answers, I'll be happy to take any.
That's lovely. Thank you, Tom. I'll just check if there are any questions in Bristol. Do we have any questions in Bristol? No, that's it. We don't have any questions online, and we will quickly go to Cambridge just to check if there are any questions there. Hi, Chris. Do you have any questions for us today?
Yes. I'm quite interested in the idea of eliminating redundant stimulus. I'm trying to figure out how that might work, because let's say we've got, I don't know, arbiter and some FIFOs and something like that, and you might find that putting in transactions A, B, and C doesn't expose a bug, but putting in transactions A, B, and a short wait and then C does expose a corner case bug. So how can you identify from your high-level stimulus what is and what isn't redundant?
So in a lot of cases, that delay there would be part of your transaction, if you will. So as you're creating stimulus, you could have a random field that would be how long do you wait from the previous one before you do the next one, and then each of those specific values would be a different path through the graph, right? So you can do things like that.
Okay, so I'd have to encode all my random delays into the graph to make that work.
In a lot of ways, yeah. At the portable stimulus level, we're not really worried about timing per se. So if you want to be able to have that level of control, you would make it part of the data structure at that level. If not, you can, when you move down to UVM, you can encode that in your driver, for example. And then you would be relying on a little bit of constrained random at that point. And so as you run your portable stimulus scenario in your UVM environment, you could run that test in UVM with multiple seeds, and you would still get different things. It's just a little bit harder to predict. So it sort of depends, as in a lot of cases, how much you want to plan for up front and how much you want to rely on the random generation.
Okay. I guess if I'm allowed a second question. So for you, inFact, to focus in on functional coverage points,
mm-hmm.
Are there restrictions on functional coverage points it can deal with then, or can I have some low-level functional coverage that's just right down and hooked up to bits of the design, telling me about FIFO depths and things like that?
Yeah, so what we do is the functional coverage is defined as part of the portable stimulus language. So if you have low-level coverage stuff in, say, your UVM model, as that we can import that into portable stimulus for you. But at the portable stimulus layer, you kind of want to stay as abstract as possible, so you don't necessarily want to rely on low-level signals, because when you go to FPGA prototyping or whatever, they may not be there, right? So as long as you're going to stay in your UVM environment, you can do that, and that's a kind of a switch that you can give to the tool to tell it which pieces you want to include and which you don't.
Okay, so it would need to be relatively high-level architectural type or something, transactional level.
If you want to be able to reuse it when you go to the SoC level, and C tests, that kind of thing, yes. But if you're talking about using inFact at the block level, which is typically where you would look for those kinds of things, as I said, we can import your existing UVM coverage points, turn those into coverage points for inFact, and generate tests that will target those at the block level. That's an example of a scenario that you probably would not reuse when you get up to the system level.
Okay, thank you.
Thank you both. We have one last online question, and that's from Grenoble. And is Constraint Explorer part of inFact or Questa?
So it's actually part of Questa inFact. So Questa is not its own product. It's a family of products. So inFact is part of the Questa family. So Constraint Explorer is part of that. The Questa simulator and visualizer are the simulator and the debug environment. We are looking at doing Constraint Explorer in visualizer, but at the moment it's in inFact. So
lovely, thank you very much. Thank you so much for your time, Tom. Today, Tom, we really appreciate it. Thank you.